You might have wondered how computers understand numbers. If you ever asked someone to show you what computers say, you might see something like, let's say, 1 0 0 1 0 0 1 1 0 0 1, or something weird like this. So when you saw that, you probably wondered to yourself, how do all the computers understand those confusing ones and zeros? Because this doesn't make any sense. This is just a bunch of ones and zeros. So let's see how. Basically, the numbers us humans understand are in decimal systems. So I'm pretty sure that decimal comes from the Latin number for 10, which would be decim, or decim. So decimal system means 10-digit system, as that means 10. Prefix is the same. So, which makes sense, because there are 10 digits, 0 through 9. So that's also why we call decimal system base 10. But the numbers that computers use are called binary, or base 2. So let's indicate that this is a base 2 number, like that. Binary, coming from bi, which means 2. For example, bicycle, two-wheeled vehicle, I guess you could call it. So computers use a 2-digit system. Excuse me. The question is, how does that 2-digit system work? Before I answer that question, let's get back to the decimal system and talk about place value. Let's pick a random number, say 37,164. So let's indicate that this is base 10. So we can break down this number into 30,000. There's some noises going on outside. Sheesh. 30,000 plus 7,000 plus not plus 6, plus 100, my mistake, plus 60 plus 4. So these are two the same, and then we can reformat this as 3 times 10 to the 4th plus 7 times 10 cubed plus 1 times 10 squared plus 6 times 10 plus 4 times 1, as 1 is 10 to the 0th. So we can write 10 to the 0th here and to the 1st there, though it wouldn't really make a difference. So do you see now why we call our number system a decimal system? It's not only because we have a 10-digit system, but because our numbers are made out of powers of 10. So now we can do the same thing with powers of 2. So for example, let's take 417, so base 10. So let's see what this would be with this little calculator over here. So let's put this in, 417. So this would be, okay, let's write that down. That would equal, this would equal 1 1 0 1 0 0 0 0 1 in base 2. So let's see why this is the case. Each digit in binary corresponds to a power of 2, just like the decimal system. So for example, the last digit in our base 2 number would mean 2 to the 0th, which is 1, and then let's say this digit over here would mean 8 because it's 2 to the 3rd, and then this digit would mean 32. So now let's look at these ones and zeros. So we can represent this binary to decimal thing, get rid of this, binary to decimal thing as a machine. The machine looks at this binary number and it says which digits are ones. So it scans this number and it sees that the first digit is a 1. So we're going right to left. So we have a 1 here. So it interprets this 1 as an on. So let's make a couple of buttons for our machine here. So we're going to need 9 because this is a 9-digit number. These may look like zeros, but they're not. they are buttons. 9. Yes. So let's see. So we have an on here. So this is on. Yes. So, oops. Sorry about that, folks. Might be impatient, but that was by accident. And then next, we have the second digit. So now we go through this and we find another one. So that's the fourth digit. And then we have some more ons. An on. You don't actually have to look right to left. You can look left to right, but that's how I sometimes do it. So the machine continues until, let's see, we have on, off, on, off, on. So remember the powers of 10 thing we did with the decimal system? We can do the same exact thing here, or we are going to do the same thing here, just with powers of 2. So the machine looks at these offs and ons, and it looks at it right to left. So this is where we look at it right to left. You didn't necessarily have to look at it right to left for this first step, but we did, and that's fine. So it says, hey, we have an on here. So this is, the machine knows that this is 2 to the 0th, or 1. So let's add a 1 down here. And then now we have a 1, and then it goes through some more digits, and then it finds the next one. So it converts this into our 32, as you remember before, because this is going to be 2 to the 5th. So we have 32, and then plus our next number, which is here. This would be 2 to the 7th, which is 128. And then the next on is 256. So then if we add all of these together, we should get 417. But why don't we check with this little calculator over here? So 1 plus 32 plus 128 plus 256 is 417, just as we expected. So that's the original number we started with. So these are the same. Put this. There we go. Equals. So that's pretty much how binary works. So let's do another example. Let's do a big number this time. Let me get a different color for this. Let's say, let's get a big number. 570,981. So, in base 10. That is a very bad underline. Sorry about that. We're going to fix that. So let's go through this. Let's put this in here. 570,981. Ooh, we're not going to write all of that down. But if we go through all of this, what are we going to have? I'm going to put our calculator out already, because I do not want to write all of that. What are we going to get? We're going to get 1 plus 4. So I'll actually leave this right here so you guys can see what I'm doing. 1 plus 4 plus 32 plus 64, 512, I believe. Yes, 512 plus 1,024 plus 4,096 plus 8,192. Oh, I'm not sure what this one is, but I'm pretty sure it's this, but if not, you guys can tell me. This last one. I don't know what this last one is, but we can check using the powers of 2. So let's count. How many is this? So this would be 0, 1, 2, 3, 4, 5, 6, 7. So this would be 19, I think. 2 to the 19th. Okay, good. We have our original number. So that is pretty much how decimal to binary works. So next time, we'll see how to convert numbers from base 10 to base 2, which is the reverse of what we just did. We did base 2 to base 10. So, hopefully this helped you all. See you all next time. Bye!